Hello, welcome to the first of our videos. We're going to start on Chapter 7, Applications of Integration. Just as a heads up, since I am filming from home, I do have a 10-month-old, so you will occasionally hear her in the background. Just sort of fair warning. She's very cute, but occasionally noisy. Okay, so Section 7.1, we look at the area of a region between two curves. So you've already seen that the area under the curve of function f on closed interval AB, in your Calc 1 course, you went over as area for that integral from a to b of f of x times dx. And this is, of course, then implying that this is the area under that curve and above the x-axis. Sketch-wise, and you'll see very quickly why I'm not an art teacher. Here is function f. Here is x equals a. Here's x equals b. F is continuous on that interval. To find the area of the shaded region, we just take the integral. The new thing we do in this section is now we add another function, say g of x. And here g of x is going to be less than f of x for all x on the closed interval AB. If you haven't seen this symbol before, the upside down capital A means for all. Well, the idea here is we know how we would find the area underneath g of x. Area underneath g of x would be integral from a to b of g of x times dx. So if I want the area only in between the two of them, which I'll highlight in red here, the idea is we take the total area and subtract off the part that we're not interested in, everything under g of x. So all you have to do is find the top function, and that will give us the area between those two curves on the closed interval. And before we get too far into this, there's also a nice little property that we have as well. If we're looking between two curves, we no longer have to care if we're above or below the x-axis. The reason is if we let f of x equal, or my apologies, let's make this cap f of x. F of x plus c1 and cap g of x equal g of x plus c1. I've basically slid them both up by the same number of units. If you're shifting, recall from your college algebra days, shifting does not change the shape of the graph. It just picks it up and slides it, in this case, just up or down based on c1 being either positive or negative. The area between them wouldn't change. If I slide f of x up by this much and g of x up by this much, the area would be the same, and in fact that will hold if we plug it into our formula as well. F of x plus c1 minus g of x plus c1 times dx. c1 minus c1 is still 0, and we get the same exact area. Integral from a to b of f of x minus g of x times dx. So slide it up or down, the area remains unchanged. All right, so a couple quick examples here. So we're going to find the area bounded by f of x is opposite of x squared plus 10. G of x is negative 3x plus 1. X equals 0 and x equals 3. You might also see instead of x equals 0, x equals 3, you may also just see this as on the closed interval 0, 3. Both of those mean kind of the same thing there. So first, we make a quick sketch of what we're looking at so that we know for sure which one is the top function, which one is the bottom function. Doesn't have to be a super detailed sketch. So f of x, opposite of x squared plus 10, so that's a parabola opening down. G of x, negative 3x plus 1. We're looking at a linear function with a negative slope, positive y-intercept. So this is the area that we're looking for. So as you can see in this one, f is the top function, g is the bottom function. So our area would be the integral from our bounds are 0 to 3 of f of x, opposite of x squared plus 10, minus g of x, negative 3x plus 1, close it up, and don't forget to multiply by dx. So then our area integral from 0 to 3 of, just a little simplifying here, opposite of x squared plus 3x, and then plus 9. So our area, negative 1/3 x cubed plus 3/2 of x squared plus 9x. And we're going to evaluate between 0 and 3. After that, it's plugging and chugging on the calculator, and we get an area of 63/2 square units. If you're not familiar with the storage feature on your calculator, I would recommend just doing 3 store as x, negative 1/3 x cubed plus 3/2 x squared plus 9x. Get a value for that. 0 store as x. In this case, the minus 0 would just drop off pretty easily. Okay, so our next one, another region. This time we're bounded by m of x, x squared plus 2x, and n of x is x plus 6. So notice here they didn't give us a left bound and a right bound. So you can see my handwriting is not super pretty. If you do have questions on it, just send me an email. I'll let you know. So first I want to know where these meet. We just set them equal to one another. X squared plus 2x is x plus 6. And we'll just go ahead and solve that one. So x squared plus x minus 6 is 0. So x plus 3 by x minus 2 is equal to 0. So x is negative 3 or x is 2. So there's our boundaries. Making a quick rough sketch. Here's our negative 1, 2, 3. Here's our positive 1, 2. X squared plus 2x. And we have our negative 2, 0. And 0, 0. It's a parabola. It's opening up. So there's function m, n of x, x plus 6, positive 6 intercept, positive 1 of the slope. There is function n. So this time the linear is the top function. So it's not necessarily the degree that tells you which is the top function, which is the bottom function. And we're meeting here at negative 3, negative 3, 3. And over here, when x is positive 2, y is positive 8. And this is then the area we're looking for. So our area would be n of x minus m of x in our integral. So n of x, our bounds, negative 3 to positive 2. N of x was, recall, x plus 6, minus m of x, recall, was x squared plus 2x. Close it up. Don't forget to multiply by dx. Top function minus bottom function. So our area this time, integral from negative 3 to positive 2. So this time we found the bounds. They didn't just hand them to us. Of opposite of x squared. Let's see, we have a plus x and a minus 2x. So minus x and a plus 6 times dx. So our area, negative 1/3 x cubed minus half x squared plus 6x. And we're evaluating those from x is negative 3 to x is positive 2. Again, the storage feature on your calculator, right above your on-off key. So for example, on this one, I would do the 2 first, to store as x, and then just key in your negative 1/3 x cubed minus half x squared plus 6x, etc. So then on this one, plugging and chugging will save you a little bit of time there. We should end up with an area of 95.6 square units. Okay, so our next one, we're going to find the area bounded by sine of x and cosine of x. So g of x will be our sine x, h of x will be our cosine x. So first, we'll just look at what's happening on the interval 0 to 2 pi. And again, as you can see from my work, it doesn't have to be a nice, neat, pretty work of art. Just sort of a rough outline to see what's happening. So I'll do my g of x in blue here. So sine of 0 is 0. And we'll count by, let's say, pi over 2 at a time. So pi over 2, 2 pi over 2 is just pi, 3 pi over 2, 4 pi over 2 is our dear friend 2 pi. So sine of 0 is 0, sine of 90 degrees is positive 1, sine of 180 degrees is 0, sine of 270 degrees, now we're down to a -1, and sine of 2 pi, we're back to 0 again. So again, just a quick rough sketch here. Then we'll look at our from the cosine. Cosine of 0 is +1. Cosine of 90 degrees is 0. Cosine of pi, then we're back down to a -1. Cosine of 3 pi over 2, 270 degrees. Now we're back at 0. And 2 pi, remember, is happening the same as what happened back at 0. So we'll make a quick sketch here. So this is our winner right in here. This closed interval. So the closed interval, notice there's two places where they meet. Well, places where sine x and cosine x are the same would be at +45 degrees, pi over 4. And at 5 pi over 4 as well. So down in Q3. So it looks like our sine was our top function, cosine being the bottom function. So our area integral from pi over 4 to 5 pi over 4 of sine x minus cosine x times our friend dx. So our area and is antiderivative of sine would be negative cosine. Antiderivative of cosine is sine. And this got brought straight down. And we're evaluating from, again, x is pi over 4 to x is 5 pi over 4. So our area then for the 5 pi over 4, we're in Q3, so minus negative root 2 over 2. So this from the fact that we happen to have a negative from our antiderivative, this negative from the fact that the cosine of 5 pi over 4 is negative. Sine of 5 pi over 4 also negative root 2 over 2. And then we do the same thing with pi over 4, which are root 2 over 2's. So minus gets brought along, and root 2 over 2 minus root 2 over 2. So we have 2 root 2 over 2 from our first batch, and minus negative 2 root 2 over 2. So 2 root 2 over 2 is just root 2, so we have root 2 plus root 2, so 2 root 2 square units. Okay. Now we do have some curves that intersect at more than just the two endpoints. In that case, we will have to sort of break them up a little bit. So if we consider f of x to be x cubed plus x squared minus x, and g of x is going to be opposite of x squared plus 2x. You can do a quick little sketch of this. If you set this f of x equal to 0, factor out an x, you do know that one of your zeros is at the origin. The other one, think of 0 is x by x squared plus x minus 1. Quadratic formula on that guy, your other zeros, x would be -1 plus or minus root 5 all over 2. So root 5, obviously bigger in absolute value than -1. So we have one negative, one positive. Leading coefficient was positive. So there's our basic idea of the shape of it. Our other one, our vertex is at 1, 1, and it's opening down. So notice for part of it, our cube is up top. For part of it, our square is up top. So we want to find these meeting places. Where do they meet? So we simply set them equal to one another to find our bounds. So x cubed plus x squared minus x is the same as opposite of x squared plus 2x. So we have x cubed plus 2x squared minus 3x is 0. Factor in x. And this is actually just factorable over the integers. Nice pretty one. So x is 0, or x is -3, or x is +1. And if you want ordered pairs on those, you can just plug them into either of the original. So one of them, they do meet at the origin, 0, 0. Our point to the right there, we have 1, 1, where they meet next. And the -3, let's see, -9 and -6, so -15. So for our area, basically we're going to have then two chunks. So we just break it up. So our first happens between when x is -3 on the lower end to 0 on the upper end, left side, right side. Function f was the top one that time, x cubed plus x squared minus x. Function g being the bottom function then. Don't forget your dx. And then we have a separate area happening between x is 0 and x is 1, with function g being the top function this time. So then our area, integral from -3 to 0 of, simplify where you can, so x cubed, that would be plus 2x squared. We have a minus x and a minus 2x, so minus 3x times dx, plus integral from 0 to 1 of basically the opposite of that, opposite of x cubed. minus 1x squared, minus 1x squared, minus 2x squared, and minus a negative x turns into a plus x. 2x plus x is plus 3x times dx. So two separate areas, and then we just find our antiderivatives. So a quarter x to the fourth plus 2/3 of x cubed minus 3/2 of x. That's getting evaluated from x is negative 3 to x is 0. And then we add on our second area. Negative 1/4 x to the fourth minus 2/3 x cubed plus 3/2 x squared. My apologies, I left off my square there. That's getting evaluated from x is 0 to x is 1. So lots of plugging and chugging later then. We have 45/4 plus 7/12 is 71/6 square units. Okay, so next up we look at horizontal rectangles. That shouldn't take too terribly long. So all of these were vertical rectangles. Occasionally it's easier to work with the other way. So our friends, the horizontal rectangles, basically instead of setting up the area under the curve with the verticals, now it will look with respect to space between the function and the y-axis instead of the function and the x-axis. So instead of a left bound and a right bound on our integral, we'll have a lower bound and an upper bound on our integral. So we'll consider y is square root of 100 minus x. And 0 to 100. Do a quick little sketch here. Here's our y is 100 minus x. So here's y is equal to square root of opposite of x. The adding of 100 will shift us to the right 100 units. So we could either do that with vertical rectangles or horizontal rectangles. And we should get the same area out of either of these. So here we're looking on 0 to 100. So if we do it with the vertical rectangles, our area integral from 0 to 100 of 100 minus x to the 1/2 power multiplied by dx. So if u is 100 minus x, du then is minus 1 times dx. So I have the dx, I don't have the minus 1. multiply by -1 inside and outside. Hopefully that's familiar to you. Integral from a to b of u to the 1/2 times du. So I'm just setting up arbitrary boundaries, and I'll plug my x back in. So our area, opposite of u to the 1/2 turns into u to the 3/2, which means I need a 2/3 coefficient, valued from a to b, but we'll put our original variable back in. So our area, -2/3 of 100 minus x to the 3/2 power, evaluated from 0 to 100. So plugging and chugging there, we get 2,000 thirds square units. Now, what if we did that same thing, but with horizontal rectangles? So a reminder, we're looking at originally y is square root of 100 minus x on 0 to 100 for the x. Well, if I solve this thing for x, y squared is 100 minus x. So x is 100 minus y squared. Now, as far as our drawing, if x is 100, y is 0. If x is 0, y is 10. So our area is the integral from, now if I'm drawing horizontal rectangles, now I want y value to y value, so 0 to 10, as opposed to the vertical rectangles where we want 0 to 100. So our function, 100 minus y squared times, instead of dx, now we have times dy. So our area, 100y minus 1/3 y cubed, evaluated from 0 to 10, and we get the exact same end result there. We get our 2,000/3 square units. So sometimes a vertical rectangle is easier, sometimes a horizontal rectangle is easier. It does vary. All right, so some problems to try out in section 7.1, 1 to 35 odd, and 47 to 49 odd. So if you have any questions, we'll go over them next class, or you can send me an email and let me know which ones you want to take a look at. And I will see you again soon. Stay safe.